So we've been talking about the types of intermolecular forces, and now we're going to look at the effects of them. So of course, just the fact that solids and liquids exist is the most important result of intermolecular forces, but other properties include surface tension, viscosity, and capillary action. Remember the video we saw with the astronaut wringing out the towel in space, and instead of falling, the water just traveled along his hands. Do you remember that? This means yes, this means no.
What would that be called when that happens in space?
Well, it's due to the surface tension of the water. The fact that it doesn't just, go off by itself, that it sticks together like that. And this is this pointer? Okay. So this is a picture of a paper clip floating on the surface of water. Should paper clips float? They're made out of metal. Metal usually sinks, right? And this isn't shaped like a boat. This is just wire. How the heck does that work, right? You've probably seen water skater bugs, little bugs that they skate along the top of the water. Well, this is due to surface tension. The fact that water makes little tiny droplets like this and that they're spherical instead of some other shape is also due to surface tension. So surface tension can be defined as the tendency of liquids to minimize their surface area. It can be quantified. You can attach a number to it. It's the energy required to increase the surface area of the liquid by a unit amount. So water has a surface tension of 72.8 millijoules per square meter. So to increase the surface area of water by a square meter, it would take 72.8 millijoules. Question?
Why is the surface tension broken when you add a drop of dish soap?
That's an excellent question. What happens to the surface tension when you add dish soap? We'll talk about that in just a minute. It interferes with the water molecules interacting with each other. So here we have another picture of a trout fly floating on the water. Even though this is more dense than the water, it floats because of the surface tension. So how does this work? So here we have an illustration. This is a two-dimensional slice of water, and we can look at these individual particles. And we talked about the water particles are attracted by dispersion forces, dipole forces, and hydrogen bonds. Right? And hydrogen bonds are pretty strong. So there's a lot of attraction between these water molecules. If you look at this molecule in the interior of the liquid, it's attracted in 2 dimensions to these 6 different molecules next to it. Of course, it's actually 3-dimensional, so you've got molecules in front and behind as well. A molecule on the surface, though, is attracted to the sides and down. There's nothing above the surface to attract it, right? So the force on these surface molecules is all to the side and down. They're pulled inward. So this molecule has a higher potential energy. It's less stable than the interior molecules. If we're going to increase the surface area of this, if we're going to have something penetrate and push the water molecules apart, that's going to cause more of the molecules to be surface molecules. That's less stable. It's a higher energy. Things don't like to go to higher energy, right? Balls roll down hills. They don't roll up hills. So everything's going towards lower energy. So lower energy is more of the molecules being in the interior of the liquid. Does that make any sense? Yeah? So in order to push these molecules apart, energy has to be exerted. So it's not going to happen spontaneously. So there's that picture from the first slide and from that video. This is a giant droplet of water. It's not even really a droplet. Not even a drop, really. What is it? A glob? I don't know, a sphere of water in space. The surface tension pulls the water together, and it always forms a sphere because a sphere is the shape that has the smallest surface area for the volume. If you take that water and you spread it out into a long rectangle or something, it's going to have a higher surface area than when it's all curled up as a ball. So it's going to form a shape that minimizes its surface area because it's a lower energy. Or you can think about the molecules are attracted to each other and they're trying to be in contact with the most molecules possible. And that happens when more of them are on the inside. Here's a spider web with little droplets of dew on it. These look pretty spherical, but you've probably seen and you maybe think of water droplets as being more of a tear-shaped, right? Let's not use red for this because water's blue, right? So, think of a water droplet as being like that, hanging off of a faucet, perhaps. Why isn't it spherical? Gravity. Gravity is pulling on it, and the reason it hangs there at all is because of the surface tension of the water. But gravity's pulling on it and distorting it, and that's why it isn't a perfect sphere. Once that falls, it will return to a perfect sphere. This water glob in space is going to be spherical when it's not disturbed. Anybody have any questions? Oh, forgot to cover this one. Surface tension will decrease as the intermolecular forces decrease. So the thing that's holding the liquid together in this sphere that's causing the surface tension is the intermolecular forces. If the intermolecular forces are weaker, like maybe you've got a polar substance but it doesn't have any hydrogen bonding, or maybe you have something that has only dispersion forces, very weak forces holding it together. Now the surface tension is much less. And so you can break through the surface of the water, of the liquid more easily. So the question was asked, what about soap? So you can try this at home. You need a very clean dish and very clean water, and you can float a needle or a paper clip on the water if you do it very carefully. You can't just throw it in there, but if you set it on there real carefully, you can do that. If you add a drop of dish soap anywhere in the water, within a very short period of time, the paper clip will sink. Same thing will happen to the bugs, the water skaters too, but that would be mean, wouldn't it? So don't be cruel to insects. So what's happening? When you put soap in here, you're disrupting the interactions between the water molecules. Now you've got something else in there between the water molecules. The soap is going to dissolve in the water, it's going to spread around, and now you're going to have soap molecules in here as well. And so that's going to reduce the intermolecular forces because now you've got different things going on there. And so that breaks the surface tension. Does that make sense? Anybody have any questions about surface tension? Viscosity, another property here. Viscosity is the resistance of a liquid to flow. And again, this is quantifiable. We should know that it can be measured. We're not going to do anything with the measurements. But the unit here is called a poise, and that's 1 gram per centimeter second. So that's how fast does this liquid flow. You can think of this in terms of honey or maple syrup. Those liquids flow more slowly, right? You try to pour honey, especially if it's a little bit cold. I mean, you tip the container and you're waiting for it to flow out, right? It flows really, really slowly. Well, this is also related to intermolecular forces. Something with high viscosity has very high attraction between the molecules. And so even though the molecules are free to move relative to each other, they're very sticky. They have high stick togetherness, and so they move past each other more slowly. And so the liquid appears thick to us. It doesn't flow easily. Something like alcohol has a lower viscosity, and so it flows very easily. It seems thin, even thinner than water. Or something like gasoline has a very low viscosity. So viscosity is going to be greater in substances that have stronger intermolecular forces, And of course, the shape of the molecule has an effect on the strength of the intermolecular forces. If we look here at a series of normal alkanes, pentane through nonane, we see that the molar mass increases, and so there would be an increase in the dispersion forces. These molecules are all nonpolar. But another thing that's going on here is that these are increasingly longer chains of carbon atoms. There's rotation around the single bonds that the carbons are attached to, and so they're a little bit like twisty snakes or pieces of cooked spaghetti. They bend and can twist around. And so nonane can become, I can't point down there. I'll talk about octane then. Pointer doesn't go to the bottom of the screen. Octane molecules, because they're twisty, can become tangled up in each other. And so in addition to stronger dispersion forces, they can just literally get tangled up. And so the viscosity there is greater than for a smaller molecule that is less tangly. Okay? Any questions? Viscosity depends on temperature. The place that I hear the word viscosity most often is in commercials for motor oil. And they talk about viscosity breakdown, and that's a bad thing, right? Viscosity depends on temperature because at higher temperatures, the particles have more thermal energy, right? You think about a substance warming up and the movement of the particles, whether they're in place or relative to each other, is a reflection of the thermal energy. It's a form of kinetic energy. So you increase the temperature, the particles have more movement. They have more energy to move, and so they will move more easily. What happens when you heat up maple syrup? It pours more easily, right? If the honey is too thick to pour, you can heat it up a little bit and then it'll pour more easily. Because now the particles have enough energy that they can partially overcome those interactions that are holding them and making them pour slowly. So this happens with the oil in your car as well. So oil in your car lubricates the moving parts. And so it needs to have a certain viscosity so that it doesn't just all run down into the oil pan. You need it to coat the parts and stay there. As the engine gets hot, the oil becomes less viscous and is more likely to just fall out. You also don't want the oil to be too viscous, because then it's all thick and sticky, and if you think about putting paste into your engine, it's not going to lubricate well. It's actually going to cause the opposite. It's going to cause more friction. So, cool thing about modern motor oils is they have polymers in them. So the polymers will coil up and become little globs at low temperatures. So, we looked at the effect of shape. So if we have two things that are kind of globs, they can contact just at a small surface area, whereas if we have two long molecules, they can have a lot more surface area where they interact, right? So at low temperatures, these polymers coil up. That reduces the strength of their intermolecular forces and reduces the viscosity. So it helps the oil to flow appropriately at low temperatures. At high temperatures, those polymers uncoil, they stretch out and become more like this, which increases the strength of the intermolecular force. And so that controls the viscosity at a higher temperature where it might become too liquidy or too inviscid. You understand that? That's pretty cool. I mean, that's chemistry making your oil better. This is a table showing the viscosity of water at different temperatures, and we see that at 20 degrees it's got a viscosity of about 1 centipoise, and as you increase the temperature, the viscosity becomes less. Now, we probably don't notice that hot water is less viscous than cold water, right? Because the difference is not really noticeable to us. But we do see the difference in something like honey or thick maple syrup or corn syrup or something like that. Any questions about viscosity? Capillary action. Have you ever seen this happen? So they prick your finger, and they just need a little bit of blood, and so they've got this little tiny capillary tube, and you touch it to the blood, and the blood just runs up it. There's no suction, nothing going on. Why does that happen? It's capillary action. Also effect of intermolecular forces. So capillary action is the ability of a liquid to flow against gravity up a narrow tube. It has to be a narrow tube. It's not going to happen with a big fat tube. It's against gravity because gravity pulls things down. You expect things to run out of a straw, not to run up a straw. So we have a combination of two forces going on here. There's a cohesive force. That's the intermolecular attractions between the particles in the liquid that hold them together. And then there's the adhesive force, the attraction between the liquid particles and the surface of the tube. If the adhesive forces are stronger than the cohesive forces, the liquid will rise up into the tube. And here we have an illustration showing the same colored liquid with tubes of different dimensions. And we see that the liquid rises much higher in a tiny tube than it does in a wider diameter tube.
Which one would have the most volume?
Which would have the most volume?
Yeah.
That's an excellent question. I'm not sure exactly what the relationship of the volume to the diameter of the tube is. That's an excellent idea. In a wide diameter tube, we think of the stupid pointer. I'll do this one because I can point here. So you've got two forces here. You've got the forces holding this liquid together. That's why it forms droplets. And then you've got the forces that cause the molecules on the side to creep up the edge. And the cohesive force is going to pull the rest of them up behind. And then you've got the opposing force of gravity pulling down. So the narrower the tube, the more effective the adhesive forces can be compared to the cohesive forces and gravity. So any other questions about capillary action? We should research that question about the volume. We've talked about the train, the very annoying train, right? You done yet? That was like an extra long one, wasn't it? We have some telepathic something going on here. So what do we call this curvature? The meniscus. And we've seen that. We've got burettes, and we're reading to the bottom of the meniscus, right? It curves up, and we're reading at the bottom of the meniscus. The meniscus is an effect of capillary action. So here, the reason that the water goes up at the edges in these tubes is because of the adhesive force pulling it up. And the cohesive force is holding it together. So here we have stronger adhesive forces and weaker cohesive forces. If we could play with mercury, which would be very fun, but unfortunately it's toxic, we would observe that the meniscus on mercury is upside down. It curves up instead of down. Because the strength of those forces, the relative strengths of those forces is different for mercury. The cohesive force is stronger than the adhesive force. And so it's bulging up, like it's trying to be a sphere, and the adhesive forces are not helping to pull it up.
So how would you measure mercury?
Well, mercury, I'd say you'd probably measure to the top of the meniscus. The glassware is not designed for measuring volumes of mercury. And so, you know, if you're wanting to measure mercury accurately with something, then you'd need to figure that out. My gut feeling would be top of the meniscus, because that's where most of it is, right? If you measure to the bottom, the edges here, then you're leaving out this part in the middle. But that would be something that you'd have to look into. Now, if you're using glass, you get a bigger meniscus than if you're using certain types of plastics. We have some plastic graduated cylinders, and the meniscus on those is flatter because the adhesive force between the water and the plastic is different than it is for glass. And there are different types of plastic that would also give you a different curvature of the meniscus.